In this video, I'll go over the method of separation as a means to solve a certain type of differential equation. We use calculus as a tool to express a function's change. We often accomplish this by expressing the unknown function with its derivatives in some way. Then by solving that equation, we then learn how and why a function would change as the input changes. As a definition then, we will say that a differential equation is just some equation and some unknown function together with its derivatives. So a solution then of that particular differential equation is something defined on a single interval that is differentiable up to the nth order and is, when substituted into a differential equation that contains up to the nth order derivative, it reduces that particular differential equation to an identity on that interval. Now, the interval itself need not be the same as the domain of the function. In fact, almost always it's smaller because it has to be a single interval. It can be open or closed, half open. It could be infinite or not. But it has various different names depending upon the book that you're using. So you could hear it referred to as the interval definition, the interval of existence. It's also called the interval of validity. It's also called the domain of the solution. These all refer to the exact same thing. For example, let's verify that the function f of x equals the square root of the quantity x squared minus 4, when defined on the open interval from 2 to infinity, is a solution to a differential equation dy dx equals x over y. To do so, it's very easy. All you got to do is just show that it has a derivative. And then when you substitute y and the derivative into the equation, it winds up being a statement that's always true for every single choice of x in the interval from 2 to infinity. Doing so is very easy. All we need to do is to verify the function has a derivative, and when you replace the function and the derivative into the equation, it reduces to a statement that's always true for every single choice of x in the interval from 2 to infinity. So in particular, clearly f prime of x is going to equal, that would be x over the square root of x squared minus 4. And that is clearly something that always exists on the interval from 2 to infinity. And if you just replace this y and y prime into the particular equation, you get that x over the square root of x squared minus 4. That's what dy dx is. That is clearly x over y, which is x over the square root of x squared minus y. You have the exact same thing on both sides. So of course, it reduces it to an identity on the interval from 2 to infinity. At the same time, I can also verify that the function f of x equals x is also a solution to the same differential equation, just on a different interval. That's also very easy to check. Just notice that if y was equal to x, then y prime would then equal to 1. And just replace all those things into the equation. You would then have the derivative, which is 1, is equal to x over y. But x, that'd be x over x. And that's certainly true as long as x is not 0. So I've shown you then two different solutions on different intervals to the exact same differential equation. This then implies that you should not expect that all the solutions look the same or have the exact same formula, because they don't have to. So we like to refer to solutions in two general ways. First, any solution in which the dependent variable, almost always y for us, is expressed solely in terms of the independent variable, most of the time that's x, and constants, it's said to be then an explicit solution. You solve y in terms of x. A relation x and y is said to be an implicit solution to a differential equation on an interval, provided there exists at least one function, even though you don't know what it is right now, that satisfies the relation as well as the differential equation on that interval. Now this unknown function, think of it as its graph is a subset of the graph of the relation. For example, let's verify that the equation y squared minus x squared equals 9 is an implicit solution to that exact same differential equation, but this time on the interval from negative infinity to infinity. To help explain it, I graph the particular relation. What I want you to do is focus on the top branch. That will then create a function y in terms of x, and in fact, it's differentiable. So let's suppose then that y is that function highlighted in the picture. I'm going to convince you that that graph, whatever it is, that its slope at every single point is given by the formula x over y. That will then show you that whatever that function is, we know then it must satisfy the differential equation, and therefore it's a solution. To do so is not difficult because we already know the equation y squared minus x squared equals 9 is actually a level curve of the function g as a function of x comma y is equal to y squared minus x squared. So because of that, using what we learned in Calc 3, to find the derivative, we just go and take the opposite of the partial of g in terms of x divided by the partial of g in terms of y. And when you simplify that, you get x over y immediately. So now if you wanted to, you could take the equation, of course, and we could solve for y. But the important thing here is that you don't have to. And in fact, many times you don't want to because you just plain can't. So you need to have some way to express our solutions without always being forced to solve for y. So just to round out these definitions, we say a family of solutions is a solution just with unknown arbitrary parameters. We almost always use C in this case, or C, D, or other letters that we need to. And then graphing these solutions just for different choices of those parameters then generate different solution curves. A parameter-free solution is called a particular solution. They almost always come from some kind of additional condition that the solution must go through some additional point. If every single solution to a differential equation, though, belongs to a family of solutions, then the family of solutions is called the general solution. That's almost always what we want to find first. We want to find the general solution, and from there, we can derive any particular solution we desire. To explain what I mean, let's suppose that y equals c times e to the 2x just happens to be a general solution of the derivative is equal to 2 times y. And let's find a particular solution that also satisfies that y is 4 when x is 1 among this particular family of solutions. So to do so, what I would do is use that when x is 1, y is 4, and then solve for the unknown constant. So y is 4. That would then equal c times e to the 2 times 1, that's 2 power. That means then c would have to be 4 over e squared. So my solution is y is equal to 4 over e squared times e to 2x. And I would probably simplify that a little bit and rewrite it as 4 times e to the 2x minus 2. That's it. That would then be a function that's a member of that family and also satisfies the additional condition that when x is 1, y is 4. That is called a particular solution. Any differential equation that can be written in the form that the derivative is equal to a function of the independent variable, in this case x, times a function of the dependent variable, in this case y. That's called a separable differential equation. And it can be solved by multiplying both sides by dx and dividing both sides by h as a function of y, and then integrating both sides. Now I'm putting that in quotations because that's totally not what's happening. It's just the algebraic manipulation result. It's not really what happens. So I'm going to show you what really happens to justify the result. So we can just, for now on, say, we'll just multiply both sides by dx for now on, even though that's not really what's happening. So, to justification. Notice on the left-hand side, that's an integration in terms of y. So y is a variable right now. But we know that we're looking for a solution to that differential equation. Let's suppose we have one. So y is a function of x. That means we can use substitution. Everywhere I see a y, I put that function of x instead, and I then make sure I change dx to be its derivative times dx. In this case, dy becomes the derivative of y in terms of x times dx. But after I do that act of substitution, I recall that this particular function is a solution to that differential equation. So I can replace dy dx with g as a function of x times h as a function of y. That means then the two portions, in the numerator and denominator, they're common terms. I can cancel them, giving me the integration that I'm interested in. So whenever you use the method of separation, you're actually doing that. It's just, it takes too long to do so. And it's easier for everyone to say, multiply both sides by dx instead. You're not really doing that. A good example of a separable differential equation comes about when you solve the exponential growth decay problem. So, in general, Let's suppose we have some quantity that either increases or decreases in proportional to its current size at any given time. That can be expressed this way, that the rate of change is proportional, that's the k, to the current size, that's y. And of course we have to have some kind of initial size, so y of 0 would be, let's say, y naught. I would want to solve that particular differential equation for that condition. This is commonly referred to as a type of initial value problem, a derivative differential equation, together with some kind of conditional for a point that the curve must satisfy. So to do that, clearly though, that if y is always 0, that's clearly a solution to the differential equation. Let's just ignore that one and look at non-zero solutions. So here's our differential equation. I'll go ahead and divide by y and multiply by dx and integrate both sides to get these two integrals. I then integrate each side. Once I've done that, I have gotten an implicit solution to my differential equation. I don't want an implicit one. I would prefer an explicit one. So let's go see if we can solve for y, being a little clever with our constants. So first, we can get rid of the natural log by exponentiating each side. Also, if you have e to the kt plus c, by using laws of exponents, you can write that as e to the c times e to the kt. But then I can get rid of the absolute value because the y then has to either equal the right-hand side or its opposite. Notice though that plus or minus e to the c, that's really saying plus or minus e to some constant. That's just some constant. In fact, the only thing it can't be is 0. But we already know that y equals 0 is a solution. So I can recover all my solutions by writing it this way, where a can now stand for any single particular constant you like. Well, but I also know that my solution has to satisfy the additional condition that y of 0 is y naught. So let's just go ahead and use that information to find out what a has to equal. So if you replace y with y naught and t with 0, you get that y naught is a. And we therefore get the general solution. This would then be the solution to the exponential growth decay problem. The difference is it's growth if k is positive, it's decay if k is negative. There are at least 2 different main examples that your book gives as a way to use the solution to the differential equation I just gave you. One was population growth and the other is radioactive materials. I'll do the second one as it's a little more fun. So in a radioactive material, that amount would decrease in proportional to its current size at any given time. Now that's because you would suppose if there's a lot of material, there's a lot of reaction. If there's very little material, there's very little reaction. So we can write that rate of change of the amount of material as an unknown constant times the amount, which in this case is y. And that gives us our growth and decay differential equation that you saw before. It's just that here I'm writing the constant as negative k, where k is positive, because I want to emphasize that it's decreasing, and also that way I can remember at all times that k is positive. The initial condition would be that the initial amount, y sub 0, is the amount we have when time is 0. We already know the solution to that differential equation. Here it is right here. Now, one clever way to use that is what's called carbon dating. In living organisms, the amount of carbon-14 in relation to the normal amount of carbon stays relatively the same during the organism's life. That's because as the amount of carbon-14 decays in his body or in the organism, it constantly brings in more from the outside. But once it dies, no more carbon is coming in. So the amount of carbon-14 decays in time. We can use that by comparing the proportion of carbon-14 in relation to the rest of the body to approximate when the organism died. Now this is a fairly good approximation to the truth, but it does assume that over incredibly long periods of time that a certain type of organism would always take in the same amount of carbon-14 and that there is about the same amount in the environment during that time. And that's true for many, many millions of years or so. But if you go too far back, it's actually not true anymore. And this doesn't work that well. Let's use carbon dating. Let's suppose that we know that the half-life of carbon is 5,730 years. That means every 5,730 years, the amount of material we had before is now half that amount. So yeah, it takes a really long time for this stuff to go away. Let's find the age of a sample that has lost 15% of its radioactive carbon-14. Well, we already know that a way to relate, to find out the amount of radioactive material in this particular organism, is given by our formula. All we have to do then is to find out what is Y naught for us and what is K in order to find out the resulting time that we want. So let's pretend that we're marking off time from the moment the thing died. Then, for the half-life, we know that after t years, only y sub 0 divided by 2 remains, because y sub naught is the amount of material we start with. So y sub naught divided by 2 is how much is left after the half-life period, whatever that amount is. If you just plug that into the equation, just replacing y with y naught divided by 2, and assuming t is then the half-life period, you can then solve for the unknown value k, or at least the relationship between k and that half-life time. Just do so by canceling the y naught on both sides, taking the natural log right away, and then just solving for t. That is the formula that relates the half-life time with the constant k in the formula. In our case, we know what t is. I just want to know what k is. So we now know what k is for this particular problem. Next, with that k, I'd like to know then, how long do I have to wait to lose 15%? Well, if I lose 15%, that means there must be 85% of the initial amount left. So, using that many years, we know that after that many years, we have to have 85% of the starting amount. That's why I have 0.85 times the initial amount. I'll just solve that for t. And remember, I know what k is. So I can cancel y naught on both sides. I can then go ahead and take logarithms of both sides. You can then go ahead and solve for t and just plug in what we know for k, and that's the exact amount. That is the number of years. So that's approximately 1,343.5 years, which is a really long time. That's how long ago this thing died. And again, this is just an approximation. Don't think this is the exact number. Another great example of going and using differential equations to model some kind of phenomenon is when you have a family of curves and you want to know another family of curves that's orthogonal to the first. So if you have two family of curves, they are called mutually orthogonal if any pair of intersecting curves, one from one family, one from the other, that they always meet at right angles. So for example, take the family of curves y equals c times x. As we replace c with different real numbers, we get just different straight lines that are all going through the origin. Now you can probably look at it and guess that a family of curves that would always be orthogonal to that family would be a set of circles that is, well, centered at the origin. I want to convince you that that is true. So let's go ahead and try to find the family of curves orthogonal to y equals c times x as c varies. To do so, let's go first find the derivative. The derivative of y in terms of x will then have to equal, well, that would just be c. Notice that's the same as though saying cx over x, and that is y over x. There's our differential equations that we keep stumbling into. Thing is, though, are curves orthogonal to this y equals cx? If they're orthogonal, that means they have to meet at a right angle. In other words, their slopes, when you multiply them together, have to be negative reciprocals. So the rate of change of our solution curves has to be the opposite of the reciprocal of y over x. That would be x over y. That is our differential equation. So we can solve that easily by just separating. So we'll have y dy is equal to negative x dx, and we integrate to get 1/2 y squared equals negative 1/2 x squared plus some unknown constant. Just bring all the variables to one side and multiply by 2 to get x squared plus y squared is just some constant. It'd be 2 times this c. So I'll call this c1. So this would then be 2 times c1, but that's just 2 times some constant. That's some constant. And that is certainly a circle centered at the origin. So the family of curves orthogonal to y equals cx is x squared plus y squared equals just some other constant. And these c's don't have to be the same. It's just a way to describe the separate families. Another great example of using a differential equation to model something would be a heat transfer problem. In particular, what we call using Newton's law of cooling. So as an example of a simple such case, let's suppose that you have a thermometer. It is currently reading 70 degrees Fahrenheit. It's then taken outside where the temperature is only 20 degrees Fahrenheit. After 1 minute passes, the thermometer now reads 50 degrees Fahrenheit. How long until it reads 25? Well, to do so, we'll use Newton's law of cooling, which basically says that the heat transfer, the rate at which heat is gained or lost, is directly proportional to the difference between the object's temperature and the surrounding medium. So if the difference in the temperatures is great, then there's a lot of transfer. If there's very little difference between the object and the surrounding medium in terms of temperature, then there's very little transfer. Now, to write that down in terms of a differential equation, if we say that y is the temperature of the object, then the rate of change of that temperature, dy dt, has to be proportional to the difference in the temperatures between the two objects. That's why I have y minus 20. Y being the temperature of the object, 20 being the temperature of the surrounding air. Notice I put a negative k. Well, negative k is still a constant of proportionality, but I want to emphasize that it's a negative amount, that it's a negative rate of change, because the temperature of the object starts more than 20 degrees. So y minus 20 is positive. So if k is going to be positive, well, then I'll make sure I put a negative in front so that we have a decreasing temperature in time. We also have two conditions this time. Actually, only one is needed and actually get the solution. We just can't get the actual final answer of how long it takes until we have another condition, because this particular differential equation will have at least two unknowns. One, the constant of integration, and two, the value of k. So we need two conditions to get rid of these two different parameters in the end. So those conditions are that when time starts, the object is 70 degrees Fahrenheit, and after 1 minute, it's 50. So let's go ahead and solve that differential equation. I'll do that by separation. I can write this then as the integration of 1 over y minus 20 dy will then equal to the integration of negative k dt. So the left-hand side is the natural log absolute value of y minus 20. That would then equal to negative kt plus c. So if I exponentiate each side, I'd have the absolute value of y minus 20 would then equal to e to the negative kt plus c. And I can rewrite that as e to the c times e to the negative kt. I can get rid of the absolute value to get y minus 20 is equal to plus or minus e to the c times e to the negative kt. Now this parameter is just this c is just some real number. So e to that is some real number. Plus or minus that is some real number, but it actually can't be 0. So for simplicity, I'll just call that a. Now right now that a then stands for everything but 0. But notice if a was 0, that would imply the equation is y equals 20, and y equals 20 is a solution to the equation. Because if you plug it in on the left and the right of this differential equation, you get 0 in both cases. So I can then allow a to be not only a positive number or a negative number, I can also allow it to be 0, and I would still get an answer. So my general solution then, in explicit form, is y equals 20 plus a times e to the negative kt. I have two unknown constants, a and k. I'll go and use my conditions to find out what they're equal to, or at least in some way use them to make the equation become simpler. The first one is when t is 0, the temperature was 70. Just plugging that into the equation gives me 70 is equal to 20 plus a times, well, just be that right, because it'll be e to the 0. So that implies that a has got to be then 50. I now know what a is in the formulas. Now I'll use that after 1 minute, it was 50 degrees. So I'd have 50 is equal to 20 plus a, which is 50, times e to the negative k. If you just solve then for e to the negative k, you get e to the negative k has got to be 3/5. Now, I could solve for k, but you know what? I don't care. I'm actually not going to do that now because I don't really need to. Instead, I'll notice a little trick that if you just take the equation, I can rewrite the e to the negative kt as e to the negative k to the t power because the powers will multiply to give me the original exponential. And that is therefore the same as 20 plus a times 3/5 to the t power. That's it. That's the formula. Where here a of course is just 50. So I'll put those 50s in. 50 and 50. Okay, well, we wanted to know then at what time would the temperature read 25 degrees. So I want to solve for t when the temperature is 25. So I'd have 25 is equal to 20 plus 50 times 3/5 to the t power. And that would then mean that 3/5 to the t power, after I subtract 20 on both sides and divide by 50 on both sides, that has to be 1/10. So that would then mean that the natural log of 3/5 to the t power would equal to the natural log of 1/10. So t times the natural log of 3/5 would then equal to the natural log of 1/10. And that means t is therefore equal to the natural log of 1/10 divided by the natural log of 3/5. And you can, of course, go and simplify that if you want to. After all, the numerator would wind up being the opposite of the natural log of 10, and the denominator winds up being the natural log of 3 minus the natural log of 5. And just by typing that into the calculator, I would get 4.5. So that's about 4.51 minutes. And that's the answer. That's how long it would take. All right, so you've seen now at least 3 different examples. Of course, we'll do more, but just to make sure you understand the method of separation, I'll do it one more time. I want to solve this differential equation, and that means I want to find the general solution. So I'd start off with that dy dx is therefore equal to x squared times the square root of y. I'd rewrite that as 1 over the square root of y dy integration is equal to the integration of x squared dx. So the left-hand side would be 2 times the square root of y. The right-hand side would be 1/3 x cubed plus c. This is actually one of those times where I probably wouldn't stop. I probably wouldn't go any further. We could divide by 2 and then take squares of both sides to get y is equal to, you'd have 1/6 x cubed plus, if this is c1, and you take that constant and divide by 2, you would then just have another constant. And we take this whole thing and we would square it. And that would be the answer. That would just be one way to represent a particular expression. You just have to be careful. To make sure that when you're done, that the quantity here is always positive. Because notice the square root, see the presence of the square root? But luckily for us here, this quantity is always being squared, so y is positive anyway. That should then be the general answer. Any type of solution should have this form. And that gives you a basic introduction to the method of separation.